Good morning. It's a pleasure to be here this morning with you and talk about a topic that I know we want to know more about. Excuse me. And that's, of course, strategies for healthcare, environmental infection prevention. Now, what I'm going to do over the next hour or so is discuss many important things with you, to include, of course, the role of the environment in disease transmission. We're going to talk a little bit about new products and processes as it pertains to infection prevention. We're going to go through some technologies for terminal room decontamination. We're going to talk about continuous room decontamination and why we need continuous room decontamination technology. And then we're going to talk about one other environmental health issue, and that's water, and that issue is heater-cooler units. Well, we have a lot to discuss, and I'm going to go through some of these things very quickly because I think you know many of these things. But some I'm going to spend a little bit more time on because I think it may be new to you. Now, I should mention that you don't have to hurriedly take notes because all of these slides will be available to you. They're going to be at a website that you're going to see in a few minutes. It's a website that's maintained by my colleagues and myself at UNC hospitals. Very simple to remember, disinfectionandsterilization.org. One word, disinfectionandsterilization.org. Okay, well, let's begin. Of course, we know in the last several years, the environment has, of course, had more data which demonstrates that it contributes to healthcare-associated infections. And last year, when I had the opportunity to talk to APIC, I talked about one of the challenges. One of the challenges, of course, is to prevent all infections associated with the environment, all infectious disease transmission associated with the environment. And we essentially made a 5-year goal. And now we're already in 1 year of that 5-year goal. So when we have 2021 to essentially eliminate all infections associated with the environment. And that's what we're going to talk about, how we're going to do that over the next 4 years. Well, you know, of course, there's increasing evidence to support the role of the environment in disease transmission. We know, of course, there's many pathogens that, of course, have an environmental mode of transmission. Things like MRSA and VRE and Acinetobacter and Clostridium difficile, norovirus, and some others. We also know that over the last 10 years, we've had very significant data as it pertains to the environment and disease transmission. That data tells us, of course, that the environment is important in the transmission of infection. It tells us that it's important for certain pathogens, which we've talked about, things like MRSA and VRE. It tells us, of course, that surfaces are contaminated. Patient rooms that are colonized or infected with MRSA or VRE or C. difficile, 25% on average of the surfaces are contaminated. We also know those pathogens survive in the environment. Those epidemiologically important pathogens survive. They survive for days, weeks, and months. We know that contact with those surfaces results in hand contamination, and of course, contaminated hands transmit epidemiologically important pathogens to patients. We also know disinfection reduces contamination, and disinfection reduces healthcare-associated infections. We now have more data than ever as it pertains to those topics. We also know, unfortunately, that rooms are not adequately cleaned, and when they're not adequately cleaned, that puts the next patient at risk for the previous patient's pathogens. For example, with C. difficile, if you or I were to enter a patient's room anywhere in this country, the previous patient had C. difficile, our risk would be 235% greater if we entered that room versus another room where the previous patient did not have C. difficile. The risk of entering a room the previous patient had C. difficile is 11% versus 4.6% entering a room where the patient did not have C. difficile previously. Increases risk 235%. That is what we, of course, have to eliminate. And of course, these are those data which I just mentioned. And of course, we know that this happens not only with C. difficile, it happens with other epidemiologically important pathogens like MRSA, VRE. Risk varies from about 50% to over 300%, essentially increasing the risk. Of course, that increased risk is associated with a contaminated environment. Healthcare workers touch that environment and transmit pathogens to the patients because of poor hand hygiene or inappropriate glove use. And of course, patients can self-inoculate organisms such as C. difficile by touching a contaminated bed rail or another contaminated surface in their room. 235% increased risk. Of course, that happens because we acquire pathogens on our hands by touching environmental surfaces, by touching contaminated equipment, and of course transmit those organisms to the patient because of patient contact, either because of inappropriate glove use or inappropriate hand hygiene. And as I mentioned, sometimes the patients can self-inoculate, all of which are important modes of transmission associated with the environment, and why, of course, environmental disinfection is so important. Now let's go to the next topic, products and practices for surface disinfection and new issues. We're going to talk about some data that we have from UNC hospitals related to new pathogens such as carbapenem-resistant Enterobacteriaceae and of course Candida auris. And we're going to talk about data as it pertains to germicides, talk about data as it pertains to UV, and of course talk about some other germicides. Now, as far as low-level disinfection of non-critical surfaces, there's the list of germicides that we have. We, of course, have things like ethyl or isopropyl alcohol, chlorine. We have, of course, phenols and iodophores and quaternary ammonium compounds. We have quats with alcohol, and I'm going to repeat essentially that quats with alcohols are not quats. You all know, of course, that we have CHG and we have CHG with alcohol. CHG with alcohol is more effective than CHG alone, or more effective than alcohol alone. The same is true with quats. Quats with alcohol are more effective than quats alone or alcohol alone. And we're going to see some data that demonstrates that. We have improved hydrogen peroxide, and of course for something like C. difficile, we have a product that is sporicidal, which of course includes peracetic acid and hydrogen peroxide. Now, the first thing that I'm going to mention is a paper that was published by Dr. Boyce in 2016, which reminds us of something that we all know. And that is, of course, we cannot over-dilute the germicides that we use in healthcare, because if we over-dilute them, of course, they're no longer going to have the microbiocidal activity that we desire. This was a paper that talked about inappropriate over-dilution of disinfectant solutions by housekeepers or by malfunctioning automated dilution systems. So this was a malfunctioning automated dilution system, those dispensers that we commonly have, of course, throughout our hospital if we're using something like a quaternary ammonium compound. The concentration of this quat was supposed to be 800 parts per million. They did an assessment using test strips, and they found 50% of the stations delivered solutions with 200 to 400 parts per million. That's one of the problems, of course, with diluting, and of course that is over-dilution. When you over-dilute, of course, you don't have a microbiocidal activity associated with your product, and of course, maybe what you're doing is just spreading microorganisms around, and possibly microorganisms are growing in that over-diluted solution, and that has been shown by various studies. As far as properties of an ideal disinfectant, we could talk about an hour on the properties of an ideal disinfectant. We don't have an hour to talk about these, but you know what these properties are. If I took 5 people aside and talked about the properties, you would come up with these properties. And of course, they include things like broad spectrum, fast acting, compatibility, and so forth. And of course, we could, we could identify how to identify an ideal disinfectant by using a scheme such as this. And we could, of course, compare 2 products, and using this scheme in a scale of 1 to 10, we could identify which product is possibly ideal for our healthcare setting. Now, as you know, all disinfectants and all processes and products have advantages and disadvantages. We're not going to spend a lot of time on advantages and disadvantages, but we know that all products have advantages and disadvantages. Quaternary ammonium compounds, you see advantages and disadvantages. The advantages include things like surface compatibility and bactericidal activity and fungicidal activity, and actually a persistent antimicrobial activity when undisturbed. Alcohols, we know, of course, they're bactericidal, they're tuberculocidal, they're fungicidal and virucidal. We also know they're fast-acting, which of course is very nice. One thing that I wanted to mention, and I've already alluded to this, is of course a quat alcohol is more active than a quat. Many years ago, we had an opportunity to study adenovirus, and the activity of various germicides, approximately 20 against adenovirus. Now, you know adenovirus is one of those hard-to-kill viruses. It's a hydrophilic virus, and of course, it's like norovirus. It's hardy and it's hard to kill. When we studied, of course, the adenovirus and many of the currently available germicides, we essentially found that a quat had a very low activity. Quat had less than a 0.5 log reduction with a 1-minute exposure time. We saw the accelerated hydrogen peroxide at 0.5% also had about the same level of microbiological activity, 0.7%. That means less than 90% reduction in 1 minute. But the quad alcohol demonstrated essentially a 4 log reduction in the same 1 minute. So quad alcohol combines the antimicrobial activity of a quat with the alcohol and is more active. Chlorine, in comparison, 5,000 parts per million, which is a 1 to 10 dilution of sodium hypochlorite that we typically buy, demonstrated a 5 log reduction. So the point is that something like quad alcohol has improved virucidal activity compared to a quat and some other products like accelerated hydrogen peroxide. As far as accelerated hydrogen peroxide, we know that it has advantages and disadvantages. The advantages include things like bactericidal, tuberculocidal, fungicidal, virucidal, and of course, safe for workers. Sodium hypochlorite, again, advantages and disadvantages. One major advantage with sodium hypochlorite, of course, is it's sporicidal at higher concentrations. And phenols also have those advantages and disadvantages. Now let's talk for a second about these products as it pertains to unique organisms like norovirus. And let's talk about norovirus as it pertains to our infection prevention practices in our hospitals. I think if you've been in infection control for more than a year, it's likely you've had a norovirus outbreak. And if you've had a norovirus outbreak, you know that 50% sometimes of the patients are infected and 50% of the staff are infected. Very, very significant, and you know you want to stop that as quickly as possible. Very, very significant. We've had them. We've essentially closed those areas to admission to new patients, and of course we want to stop it as quickly as possible. And of course you know one of the reasons that it's so infectious and capable of transmitting disease, of course, is it has a very low inoculum or a very low dose. It only requires 18 viral units or virions to cause infection. And that's why, of course, we have to be very, very effective in our reduction of contamination with norovirus, as well as, of course, other pathogens in healthcare. At UNC hospitals, when we have patients on contact enteric precautions for C. difficile or norovirus, we essentially use chlorine. The reason we use chlorine, of course, it's the most robust antimicrobial product. We don't use a product that has limited antimicrobial activity or antiviral activity. We want to essentially use the most effective product and the product that has been proven several times to control outbreaks and, of course, an outbreak setting. So we use chlorine. I want to mention one of the reasons that we use chlorine. It's shown nicely in this paper that was published several years ago. I think it was 2015. This is essentially looking at products like quats, accelerated hydrogen peroxide, and chlorine. And what this paper showed is accelerated hydrogen peroxide and quats were less effective in 10 minutes than sodium hypochlorite in 1 minute. Quats, accelerated hydrogen peroxide, were less effective in 10 minutes than sodium hypochlorite in 1 minute. Now, I'm not sure how well you can see that bar, and let me kind of explain what's over in that red bar area. Essentially, that's data which shows that if you use something like a sodium hypochlorite at 5,000 parts per million, at 1 to 10 dilution, for 1 minute, you essentially see almost a 7 log reduction. That's a 99.99999% reduction. If you use that same inoculum and you look at something like accelerated hydrogen peroxide at 0.5%, you may be able to see it takes 10 minutes to get a less than 3 log reduction. 10 minutes for a less than 3 log reduction. Of course, the same is true for quat. Essentially, quat alone, you have essentially 10 minutes for a 2 log reduction, 99% reduction. So you essentially see here the importance of a chlorine-containing product in eliminating, of course, a pathogen such as norovirus, and the robustness of chlorine compared to essentially the robustness of other products such as a quat or a accelerated hydrogen peroxide. You may also notice in the legend there, it talks about a quat alcohol containing 2,000 parts per million of a quat and 70% ethanol, was effective in inactivating the murine norovirus, which is an excellent surrogate for human norovirus, in 5 minutes. Okay, let's talk about some emerging pathogens real quickly. Emerging pathogens, Candida auris. Of course, we know there's a lot of concern about Candida auris. We know it's, of course, a lot of concern, and I'm going to show you some research studies that we've done. Now, this is, of course, me. It's not the researcher that has done the studies. The researcher is actually much more attractive. Her name is Maria Gergen. Maria has worked with me for 30 years, but I, of course, have to show myself before I show the work that she's done. She, of course, has done a number of studies with us, a wonderful person at UNC hospitals. I frequently tell her I talk about the things that she does for me. So today I'm going to talk about the things that she did as it pertains to inactivating Candida auris. And we're going to look at essentially some data. And we're looking at data essentially 1 minute inactivation using a 3-log reduction as a benchmark, using a very difficult test called a quantitative carrier test. And of course, we're looking at it in the presence of fetal calf serum. And what you can see if you look down that slide, of course, is a number of germicides are active against the Candida auris. The germicides include things that you would expect, things such as peracetic acid and glutaraldehyde, and hydrogen peroxide, and of course, peroxyacetic acid. You can also see that quad alcohols are effective. You can, of course, see that isopropyl alcohol is effective. You can see that a 1 to 10 dilution of chlorine is effective. You can see that an ethanol hand rub is effective. And you can see that accelerated hydrogen peroxide is effective. Those products killed in 1 minute greater than a 3-log reduction. That's a 99.9% reduction. So if you had 1,000, you're down to 1 with this particular methodology and, of course, these particular germicides. Now here you see what did not kill Candida auris in 1 minute. You see things like actually orthothaldehyde did not kill in 1 minute. We actually tested orthothaldehyde in 5 minutes. It killed in 5 minutes, not in 1 minute. Slow acting. We see essentially 3% hydrogen peroxide. We see quat. We see povidone iodine. We see a lower concentration of chlorine, 1,000 parts per million, not 5,000. We see 2% chlorhexidine glutenate, 4% chlorhexidine glutenate. We see 0.5% triclosan, 1% CHG with alcohol, and then 1% chlorozanol. So some products did not, some products did. And of course, many of the products that did are the products that we commonly use, to include ethanol hand rubs, to include alcohol quats, to include, of course, other products as well. As far as carbapenem-resistant Enterobacteriaceae, we've looked at 3 different types of carbapenem-resistant Bacteriaceae. We've looked at an E. coli, a Klebsiella, and an Enterobacter. And again, you see essentially kind of the same antimicrobial pattern. You essentially see, again, the high-level disinfectants being effective. You see quad alcohols being effective. You see, of course, products like phenol, chlorine, isopropyl alcohol, the ethanol hand rub, all effective. You also see at the bottom there the quat. That is not the quad alcohol, but only the quat was effective against the carbapenem-resistant Enterobacteriaceae. The other thing that I wanted to mention are some studies that Maria did at UNC hospitals on germicidal activity of UVC against Candida auris and compared it to Candida albicans. And we see in this particular study, which used a technology, which used the TruD technology in a bacterial cycle, not the sporicidal cycle, the bacterial cycle, which has a 17 to 19 minute cycle and has a dose, of course, that is being delivered of 12,000 megawatt seconds per centimeter square. You see again good activity, very good activity against Candida auris and almost comparable to Candida albicans. You see overall about a 3.5 log reduction. Good activity again with a particular UV technology. Now let's go on. Let's talk about other things. We know, of course, that we need to, of course, make these surfaces devoid of microbial contamination to the greatest extent possible. We don't have to sterilize surfaces, but we're going to make them hygienically clean, which we'll talk about in a second. Of course, what we need to do is we need to, of course, clean all touchable hand contact surfaces. They should be wiped with a disinfectant. We do not emphasize high-touch surfaces. We did a study that showed that essentially the microbial contamination on high, medium, and low-touch surfaces was not statistically different. High, medium, and low-touch surfaces had the same level of microbial contamination. That's why we emphasize all hand contact or touchable surfaces. Also, we don't want to emphasize high-risk objects. No one has identified what a high-risk object is epidemiologically. You or I can essentially identify what we think it is, but that has not been determined in the scientific literature. So we really need to concentrate not on high touch, not on high risk. We need to concentrate on all touchable hand contact surfaces. And as you know, when we clean in the United States, it's a one-step process with a disinfectant detergent. There's no pre-cleaning necessary unless, of course, there's spill or gross contamination. Now, things have happened since, of course, the CDC guideline was published in 2008. We know more, and thank goodness we do. One of the things we know more is that, of course, it's better to do at least a daily disinfection. There's 2 pieces of evidence that says that we should do daily disinfection of environmental surfaces. When I and colleagues wrote the CDC guideline many years ago, we didn't have this evidence. So essentially, we couldn't say that daily disinfection was recommended. Now there are evidence, there's 2 pieces of literature that talks about the benefit of daily disinfection. You see those large black bars? Essentially, that's the frequency of glove contamination when you only clean when the surfaces are soiled. Now, you may not even be able to see the hollow bars, but the hollow bars are essentially the frequency of hand contamination when you clean daily. So if you only clean when surfaces are soiled, there's a lot more surface contamination and hand contamination associated with those surfaces, shown for C. difficile and shown for MRSA. So we have data demonstrating daily disinfection. Now, all of this information supports comprehensive disinfecting regimens. But of course, we know that we have to improve as far as the comprehensiveness or the thoroughness of our cleaning. We have data that demonstrates, of course, that daily cleaning is actually poorer than terminal cleaning. Daily cleaning, the frequency of thoroughness, it may be 30% of the surfaces are clean. For, of course, terminal cleaning, maybe 50% of the surfaces are clean. That means that anywhere from 70 to 50% of the surfaces remain contaminated, and a reservoir for pathogens for touch contamination and transmission, of course, to patients. So, of course, we need to, improve our thoroughness of cleaning. Thoroughness of cleaning can be improved by monitoring the thoroughness of cleaning. It can be monitored by things such as ATP bioluminescence, and can be monitored by mechanisms such as fluorescent marker. The fluorescent marker is a transparent, easily cleaned, environmentally stable marking solution that fluoresces when exposed to an ultraviolet light. Of course, there are comparisons in the literature regarding fluorescence and ATP. We recently presented here at the APIC meeting in 2017 data which of course discusses these 4 markers, and we found that the fluorescent marker is a more useful tool in determining how thoroughly a surface is wiped and mimics the microbiological data better than ATP. Now you can see on the far right, that's the microbiological data, 97.7%. You can see essentially fluorescence, 70%. That essentially tells us that fluorescence is a better marker of microbiological data than ATP. At 250 relative light units, it was only 13.2% compared to microbiological data, and at 500 relative light units, it was 26%. The better marker of thoroughness of cleaning is, of course, fluorescence in this particular study. Now, we should not think of ATP as a microbiological marker. Of course, it is not. It is not sold as a microbiological marker, but sometimes I think we think of it as a microbiological marker. It is not a microbiological marker. It is a marker of organic debris on a surface. This is essentially a scatter plot that essentially shows no statistical correlation between ATP levels and standard aerobic plate counts. We have put on a surface as many 10 to the 4th, 10 to the 5th, 10 to the 6th, that's 10,000, 100,000, a million microorganisms on the surface, sampled the surface with ATP, and of course, the level of contamination was less than 250 relative light units. That is, it was a negative ATP with as many as 100,000 or 1 million microorganisms on surfaces. It's not intended to mark microbial contamination. It's intended to mark, of course, organic debris, and that's what we have to keep in mind. How about the future and the future methods to ensure thoroughness? There is some technology that's not yet been incorporated into healthcare. I hope it is. I've been asking companies for about 20 years to develop this technology. It's used in paint, but essentially it's technology that essentially when you apply a product to a surface, it is colored, for example, blue, and then it fades to essentially a non-existent color. That is, it fades back to the original color if it's white or whatever color it is. So this is a color fading time which can be matched possibly to a contact time. So this is not yet available, but I hope it becomes available, because what would it do? It would allow, of course, environmental services to know where they have been, what areas they have essentially covered and what areas they have not covered. And of course, it fades, so the original color returns to the surface, and it can be used as a marker for thoroughness of cleaning, and possibly in the future as a marker for, of course, a certain level of antimicrobial kill. So possibly in the future that will be available. Very quickly, we're going to talk about technologies for terminal room decontamination. We're not going to include technologies with limited data. We're going to look at technologies which have a very significant amount of microbiocidal data and infection reduction data, and that is, of course, UV and hydrogen peroxide type technologies. Again, we're not going to discuss technologies with limited data. Now, of course, you know we call these non-touch because they're mechanical systems. Of course, we have wiping, which is a touch system, and then we have non-touch, which is mechanical system. Now, with these non-touch technologies, I think you all know that this supplements but does not replace surface cleaning and disinfection. We continue to do surface cleaning and disinfection. This supplements essentially that surface cleaning and disinfection. And what does it do? It kills those microorganisms that are remaining after surface disinfection. Whether it's 50% thoroughness of cleaning by surface disinfection or 80% thoroughness of cleaning, there's microorganisms that remain. This technology kills those microorganisms, which makes the room safe for the next patient. So no longer will we have a 235% increased risk for something like C. difficile. Now, when we evaluate technology at UNC hospitals, we use this parameter. We essentially said we want technology that is safe, we want it to be microbiocidal, we want it to reduce healthcare-associated infections, and we want it to be cost-effective. So let's see how we're doing with that, those parameters as it pertains to essentially UV and hydrogen peroxide. We're going to go through this quickly. Again, all these slides will be available to you, but essentially this is just showing there's lots of data which demonstrates the microbiocidal activity of UV. Data exists on carriers, data exists in patient rooms. The data involves all the multiply drug-resistant organisms, all of the epidemiologically significant pathogens. We also have data which demonstrates a reduction in HAIs. We don't only have microbiocidal inactivation data, we have, of course, data resulting in a reduction in HAIs. And you can see here that there were 5 studies that have been published in before and after study design, and one study that we're going to look at real quickly, which is a randomized controlled trial, which was just published a couple months ago in the journal Lancet. And of course, this is sometimes referred as the better disinfection study, benefits of enhanced terminal room disinfection study. What was done in this particular study, it was done between North Carolina and Virginia. It was done in collaboration between Duke and UNC. And of course, we had a 2x2 factorial design. We had quartz alone, quartz with UV, chlorine alone, and chlorine with UV. And so essentially what we did is we enlisted like 20,000 patients over a 2.5-year period of time. This study took over 2.5 years, cost $2.5 million, and evaluated essentially the benefit of the possible benefit of enhancing room decontamination by no-touch technology. Now you can see the way this works. You have a patient in a room, and the patient is discharged. And then you have the room disinfected. Depending on which phase of the study a hospital was in, there were 9 hospitals, it would determine how the room was being disinfected for that 6-month period of time. If the hospital, like UNC hospitals, was in the quat phase, then the room would be cleaned with quat. If they were in the quat UV phase, then it would be cleaned with quat UV. Then the patient was monitored. The patient was monitored for essentially acquisition of the previous patient's pathogen. Now the patients over on the far left, are patients that are colonizer infected with these epidemiologically important pathogens. So these were all on contact precautions, things like Acinetobacter, MRSA, VRE, and C. difficile. Patient was discharged. Of course, a room was disinfected. Then we monitored the next patient in that room for the previous patient's pathogen. Was the previous patient acquiring that is the next patient acquiring the previous patient's pathogen. Of course, with C. difficile, since we didn't want to clean rooms with quat or quat UV, essentially we only had 2 options. The C. difficile patients only had chlorine and chlorine UV. Again, this was a 28-month period of time because essentially we had 6-month test periods with a 1-month washout period. And these are the data. We don't have to spend a lot of time on the data, but essentially what the data demonstrated is enhanced terminal room disinfection strategies decreased the clinical incidence of target multiply drug-resistant organisms by 10 to 30%. So all the enhancements had an overall reduction of 10 to 30%. The highest reduction was in the quat UV group. Now let me show you one other thing, and this is probably going to be hard for you to see, but I'm going to try to explain it to you. These are data which essentially looks at enhanced disinfection leading to reduction of microbial contamination and decrease in patient colonization infection. I'm not sure how well you can see it, but at the top it talks about epidemiologically important pathogens. And you may be able to see, some of you, a number of 60.8. That's the number of epidemiologically important pathogens we found with 5 Rodax in these patient rooms that were being evaluated on contact precautions. Then you may be able to see much smaller numbers over to the right of that number. Numbers like from 60 to 3, from 60 to 11, from 60 to 3. So essentially those enhancements resulted in a 80 to 94% reduction in microbial contamination. Enhancements resulted in an 80 to 94% reduction in microbial contamination. Now the question is, did that result in a reduction of HAIs? For the very first time, there are data which demonstrates in the same study that as you reduce essentially microbial contamination, you reduce the rate of infection, because below that you'll see essentially the colonization infection rate for the standard method, which of course was quat, was 2.3%, and then you see the enhanced methods. The infection rate went down to 1.5%, a 35% decrease, and that was related to a decrease in microbial contamination. So you can see that a decrease in microbial contamination is directly related in the same study to a decrease in healthcare-associated infections and colonizations. That's what this study did. First study which quantitatively described the entire pathway whereby improved disinfection decreases microbial contamination, which in turn reduced patient colonization and infection. So we know from this, decreasing the microbial load decreases healthcare-associated infections. Now, of course, you know that all these technologies have advantages and disadvantages. We're not going to have time to review those advantages and disadvantages. Of course, with hydrogen peroxide, we have the same type of data, very good microbiocidal data, very good infection reduction data, and again, there are disadvantages and advantages for that technology as well. One of the disadvantages for hydrogen peroxide is time. It takes a longer time, of course, than ultraviolet light, but they both have the disadvantage that essentially you cannot be in the room. You cannot be in the room when these technologies are employed, so we're looking for continuous room decontamination technologies, and we're going to talk more about that. So essentially this technology should be used. If you're not using this technology, you should essentially make a request to, of course, your capital equipment budget. Of course, we compete for dollars like everyone else competes for dollars with capital equipment, but you should use the data that we just saw, the HAI reduction data, to essentially support, validate, provide justification for essentially implementing this type of technology for terminal room disinfection for, of course, after discharge patients on contact precautions. Of course, you should use the peer-reviewed literature in selecting the process that you want to do or use. You should, of course, use devices that have demonstrated bactericidal or microbicidal activity, either, of course, using carrier test or patient rooms. And, of course, ideally, as it says on the last bullet there, one should select a device that has demonstrated bactericidal activity and demonstrated the ability to reduce HAIs. Okay, now a few minutes ago we mentioned the word continuous room decontamination. What are we talking about? We're talking about essentially technology that essentially people can be in the room when this technology is working. As many of you know, we refer to, of course, daily cleaning as the trash and dash. Daily cleaning is not like terminal cleaning. Daily cleaning is very quick, and a lot of surfaces are not, of course, disinfected. Of course, those surfaces remain contaminated and a reservoir for epidemiologically important pathogens, and can be a reservoir for pathogens so that touching that surface can result in transmission when there's poor hand hygiene or inappropriate glove use. So what we have here is as how we would prevent infections associated with the environment. Well, first of all, we have to ensure the use of safe and effective low-level disinfectants. We talked about that. Secondly, we have to ensure that there's thoroughness of cleaning. That's really very important. If we're only cleaning 30% of our surfaces, 70% remain contaminated. We need to thoroughly clean surfaces. Then we can see we use the no-touch technology. The no-touch technology, of course, will make that room safe for the next patient that's entered. So no longer is there a 200 or 300% increase of risk because a patient enters a room where the previous patient had an epidemiologically important pathogen. But that's not enough. We need to do one more thing. We need to essentially develop and use continuous room decontamination technology that continuously reduces microbial contamination. And we need a eureka event here. We need essentially something that essentially allows us to continuously decontaminate rooms. Now, we're not trying to make these rooms sterile. We're trying to make these rooms hygienically clean. And by that we mean essentially we want them to be free of pathogens in sufficient numbers to prevent human disease. So that's what we're trying to do. And we're going to talk about some of these technologies, and then we're going to end real quickly on the topic of heater cooler units. Some of these technologies, why do we want continuous room decontamination technology? Well, of course, it allows for continual disinfection. Of course, it can allow for patients and staff and visitors to remain in the room. It does not require an ongoing behavioral change. And once it's in place, it's self-sustaining. It continually decontaminates the room. That's what we're looking for. What are the disadvantages? Again, everything has advantages and disadvantages. The disadvantages include things like room decontamination. The biocidal activity is slow. These are not going to kill the microorganisms in 15 seconds, 30 seconds, a minute, like we talked about before. These technologies are going to kill in hours, maybe 12 hours, maybe 15 hours. But it's going to kill in hours, but it's going to do it continuously when it's in the room. Let's first talk about visible light disinfection in the patient room. Essentially, we have visible light. Essentially, we have a white light and a blue light. Essentially, you can see the blue light is obviously distinguishable from the white light. When you have blue light, you have essentially increased irradiance and you have increased kill. And we've had an opportunity to evaluate these white lights, blue lights, and essentially this wavelength of visible light that kills microorganisms. Essentially, the way this works is it has an automatic switching mode between a switch that essentially allows you to convert the mode by a wall-mounted control. And I know these charts are kind of meaningless to me for the most part. We had a PhD biostatistician create a model that essentially modeled inactivation compared to control using this white light and blue light. And essentially what the model told us is that the model demonstrated improved inactivation of pathogens with both the blue and the white light. Now, the pathogens that we use are the pathogens, of course, that are epidemiologically important. We use things like multiply drug-resistant Acinetobacter, MRSA, VRE, and Clostridium difficile. Of course, the blue light, which has a higher radiance, of course, kills better than the white light, but both of them are actually killing. They can be in the, on 24/7, 365 if you don't mind the light. Now, obviously, if persons don't want the light on, possibly at some point there could be a remote control. When the person is out of the room, the light could be on. When they're in the room, possibly the light could be off. Now, I'm not sure how well you can see this, but essentially over on the far right, there's a number 90%. And that tells you essentially the time to achieve a sustained microbial reduction for each one of those pathogens. So for MRSA, you may be able to see that you get a 90% reduction using white light in 24 hours. With blue light, it takes 10 hours. 90% reduction with white light 24, blue light is 10. Now, if you walk down that far right column, you'll see something like multiply drug-resistant Acinetobacter, 90% reduction for white light 14 hours, for blue light 15 hours. So essentially those are the hours for an activation of 1 log or a 90% reduction of epidemiologically important pathogens. Now, obviously there are advantages and disadvantages to everything. Some of the advantages of this, of course, it could be accomplished, it could be 24/7, it could be on all the time, or you could have some type of remote control mechanism that essentially allows it to be on when the person is not in the room, and off if the person is bothered by the light when they're in the room. Of course, unlike UV and hydrogen peroxide, everybody can be in the room. There's no restrictions. It's not harming anyone. I was in the room with these lights for 2 years, and so far I'm okay. Disadvantages, it has not been demonstrated to reduce HAIs. We're going to do a little study trying to get better at that particular question, but it has not been demonstrated to reduce HAIs. Another technology, real quickly, that we've been investigating, essentially what it does is it takes oxygen and water out of the air and makes hydrogen peroxide in low concentrations. The concentration of hydrogen peroxide is not harmful to people, but it kills microorganisms. The concentration that you want to have is a concentration of like 0.2, 0.3 parts per million, and of course it would kill microorganisms. So this technology is being evaluated. Essentially it could be placed, for example, in a duct. It could be a standalone device, but so far we have not found essentially a product that produces a low concentration of hydrogen peroxide that effectively kills microorganisms. We've tested one for several years, and essentially it did not demonstrate a microbiocell level of hydrogen peroxide. So we're continuing to evaluate that. Another is surface disinfectants and persistence. We have been looking, my colleague Maria has been looking for a persistent antimicrobial for at least 15 years. We've tested every persistent antimicrobial that has been offered to us. As you know, most antimicrobials do not have long-lasting or persistent or sustaining antimicrobial activity. They work well at time 0, but they don't have a continued antimicrobial activity. We're looking for essentially an antimicrobial that if placed on a surface would essentially continue to have an antimicrobial activity for 24, 48 hours, 72, 96 hours. It would not affect essentially how we did disinfection in that patient care area. We would continue, of course, to do daily disinfection, but we would have as a backup this persistent antimicrobial on a surface. Several years ago, we investigated a product called Surfacine. Essentially, it worked for up to 12 days. Even then, when we wiped it with things like water or quaternary ammonium compound, it continued to have an antimicrobial activity. This product contains silver, and for that reason, it was a little bit too expensive to market. We've essentially looked at quaternary ammonium compounds, and I'm not going to be able to explain this slide to you because of time, but I wanted to mention that when we put a quaternary ammonium compound, for example, on keyboards, as long as that quat remained there undisturbed, it continued to have an antimicrobial activity. Now, once it was disturbed by people typing or essentially removing the quat from the surface, it no longer had a sustained antimicrobial activity. So it's not bound to the surface in this case. We want something that's bound to the surface and has a persistent antimicrobial activity. So essentially we can persistently, in a sustained way, can kill microorganisms. There is a paper that is published, and we're going to investigate this technology as well as another technology looking at essentially self-disinfecting coatings or persistent antimicrobials. There's going to be, of course, this opportunity to apply a disinfectant where it's going to have a sustained antimicrobial activity. So again, the surface will not be a reservoir for infectious agents. Of course, there's a study that I alluded to. In this particular study, it was done at the University of Arizona. They did show essentially numbers, 99.9% reduction at 4 weeks after treatment, 99% after 8 weeks, 99% after 15 weeks, but it must be reapplied every 3 to 4 months. We're going to continue to look for products that have sustained antimicrobial activity or persistence. Of course, we have these technologies. I mentioned visible light disinfection. We found that that's effective. I talked to you about that. We want to essentially continue to investigate technologies that can be applied to the room that would be effective without harming, of course, people. And of course, we're looking at self-disinfecting technologies such as antimicrobials added to surfaces. We're also looking, of course, or others have looked more correctly, at surfaces such as copper. Now, all of these, of course, and the reason for possibly using these is a continuous disinfection system, obviously, and of course, you can be in the room during this. It's unlike the no-touch technologies where you can, of course, not be in the room during the use of the ultraviolet and the hydrogen peroxide vapor technology. We mentioned copper. Copper, of course, there's data on copper and, of course, data demonstrating the microbiocidal activity of copper and some data on infection reduction. So far we've done all those things except for looked at healthcare environment issues. This topic is essentially environmental infection prevention strategies, so I thought I would talk about water as the last thing that we're going to discuss. And I want you to mention to you that there recently, of course, is a paper that looked at all the outbreaks associated with water reservoirs in a healthcare setting. So this particular paper, which was published in Clinical Infectious Diseases, looked at all of the outbreaks with a water reservoir and listed all of the outbreaks with a water reservoir. It talked about, of course, the organisms. It talked about transmission pattern, population affected, the type of infection, whether molecular typing essentially validated the involvement of water in disease transmission, and of course, the type of outbreak and the number of people that were involved. As you might suspect, Mycobacteria was a very common genus associated with water outbreaks. A number of Mycobacteria were involved and a number of sources were involved. The one source that we're quickly going to mention is the heater-cooler units. Of course, we know that there's been a global outbreak of heater-cooler units affected with Mycobacterium chimera. Of course, this has happened all over the world. Of course, hospitals that do cardiothoracic surgery have been affected by this because a very commonly used heater-cooler unit, the Sorin, has been identified as a point source of Mycobacteria, which has resulted in an aerosolization of the organism and, of course, a settling on the wound of patients that are undergoing cardiothoracic surgery. So there has been a very significant series of outbreaks, and of course everyone is trying to implement infection prevention strategies to minimize transmission. These outbreaks have been very well published now. They've been in a number of US journals and a number of journals in European countries. Of course, you may know that it really began in Western European, or really was recognized first in Western European countries, and then of course we recognized it in the United States. Now, of course, the non-tuberculous Mycobacteria are very significant microbes associated with water. They've been involved, of course, with a number of outbreaks, which we alluded to. The reason for that is, of course, they grow well in low organic carbon conditions. They're relatively resistant to disinfectants. They like to adhere to surfaces and form biofilms. The disinfectants that we may be using kill off the other microorganisms, and of course, since the mycobacteria are relatively resistant, they survive in those settings, and of course, they were the organisms associated with these heater-cooler unit outbreaks. Of course, as you know, there have been a number of CDC guidelines related to this, and of course, there have been guidance associated with the heater-cooler units from the manufacturer of these units, Sorin. And of course, those guidelines include things like using filtered tap water and of course, doing disinfection of the system, and of course, some other things. I just wanted to mention one thing that we may have done that is a bit unique. Of course, we were very concerned about transmission of course, Mycobacterium chimera associated with heater-cooler units. The one thing that we did, of course, is we followed all the Sorin recommendations as far as things like filtered water and disinfection. But we also did some other things that were recommended to include, of course, we pulled those heater-cooler units, or we exhausted those away from the patient as far away as possible. And fortunately for us, that has always been the case. The other thing that we did, which maybe is a little bit unique, is we have placed HEPA units, portable HEPA units, adjacent to these heater-cooler units. The portable HEPA units, of course, are very effective in essentially cleansing the air of microbial contaminants. And I'll show you a slide in a second. But the other thing that, of course, you can do is you can place these heater-cooler units in a room adjacent to the operating room, so essentially the exhaust is not being exhausted to the OR and possibly exposing the patient and the patient's cardiothoracic incision with the contaminants from the heater-cooler unit. Well, this is a type of portable HEPA unit you can place adjacent to the heater-cooler units. This unit has been evaluated and shown essentially to be extraordinarily effective in removing microbial contaminants away from essentially the air that in this case is being generated from the heater-cooler units and the contaminants associated with this heater-cooler unit air. So what have we done? Remarkably, we've done it in 55 minutes. We've looked at the role of the environment in disease transmission. I hope I've provided you convincing evidence that now more than ever before, we have very convincing evidence of the role of the environment in transmission and the importance, of course, of very effective surface disinfection. You know, surface disinfection includes a good product, but it also requires a good practice. So product plus practice equals essentially perfection. You can have the best product and have a bad practice, and you're certainly not going to have an effectively disinfected surface. Product plus practice equals perfection. As far as new issues, we talked about, of course, the new pathogen that we're all concerned about, Candida auris, and talked about the germicides that kill it, and of course the UV that may be effective, that is effective as well. We talked about, of course, the carbapenem-resistant Enterobacteriaceae and saw that most of the germicides we commonly use every day are effective. We talked about technologies for terminal room decontamination. We talked about, of course, UV. We talked about hydrogen peroxide. And of course, we talked about those technologies should be implemented to essentially prevent transmission of infection associated with inadequate cleaning of rooms at the terminal or discharge cleaning. And then we talked about some new technology that I hope will be available in the next 3 or 4 years. That could be continuous use technology, continuous room decontamination technology, and we talked about several options that we probably will have to include light disinfection, to include low concentrations of hydrogen peroxide, to include self-disinfecting surfaces, and possibly other technologies such as copper. And lastly, we talked about other healthcare environmental issues. Now, of course, we still have our challenge. Last year, we talked about a challenge of eliminating the environment as a mode of transmission in 5 years. Well, last year was 2016. We're already into 2017. We only have 4 years left. So essentially, we have to do all these things. We have to ensure the use of safe and effective disinfectants. We have to ensure the thoroughness. We have to implement no-touch technology, and we have to investigate new continuous room decontamination technology and implement that technology when it's shown to, of course, be safe, to be microbiocidal, hopefully reduce HAIs, and of course, hopefully be cost effective. And of course, lastly, we talked about water reservoirs, and of course, water reservoirs present an unacceptable risk of infection. We have to remain cognizant of water reservoirs. They're all around us in healthcare. They've been associated with literally dozens and hundreds of outbreaks. And of course, now we have a problem with heater-cooler units, and we have to effectively protect our patients by using technology that intervenes in transmission of infection. So with that, please write this disinfection and sterilization. That's not hard to remember. One word, disinfectionandsterilization.org, and you'll get all these slides. And thank you very much for waking up so early and being here.